Hi, guys. This is the second half of lesson 1.3. We're going to continue learning about electron configurations, orbital diagrams, and then we're going to move on to talk about trends in the periodic table, just like you learned about in grade 11, but with the quantum mechanical model of the electron in mind. So, in front of you, you need to have some paper, a periodic table, and something to write with as well. Uh, on our last lesson, we talked about the differences in energy of the different orbitals. So take a second and see if you can write the electron configuration for calcium. Pause the video here and try that. Okay, so you should have written for calcium 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. In order to know what electrons go in which orbital, you probably consulted the slide before this or looked at the graph that's on the handout I gave you the other day. So remember that this is an electron configuration. If I wanted to write the shorthand form of this, I could write square brackets with the noble gas that appears before calcium. So that's argon. And here, then I just write the orbitals that occur after argon. So that's 4s2. Again, this is how we write electron configurations. If I asked you to draw an orbital diagram, I'd be asking you to draw the little boxes that go along with them. So, orbital diagram for calcium, well, I know that there can be two electrons that go in 1s. I know that there can be two electrons that go in 2s. Remember, they both have to be spinning in opposite directions. That's why my arrows point in opposite ways. I know that there are three 2p orbitals, and I have 6 electrons in them. Note that I draw the electrons first in each individual orbital before I show them paired. So there we've got our 2p orbital. Then I've got 2 electrons in 3s, again spinning in opposite directions, and 3p. Here, again, the orbitals fill, or the electrons fill each individual orbital individually before they are paired. And note that I just said fill the orbitals. We remember that this is just a model, right? They're not empty boxes to be filled. Just kind of talk about them that way. Then we have our 4s orbital, and we've got 2 electrons in that. So this is the long form electron configuration for calcium. This one here is the short form electron configuration for calcium. And this is the orbital diagram for calcium. Okay, so before we jump into talking about scandium, we're going to take a look at our periodic table. So first, find scandium on your periodic table. Mm. And I have to figure out how to get rid of my pen. Okay, so here's scandium on our periodic table. Wouldn't it be nice if I didn't need to consult that little diagram at the beginning of this slideshow every time I wanted to draw an orbital diagram? You can use the periodic table to help you remember the order of the orbitals. So scandium is down here, it's element 21. Scandium has 2 electrons in 1s. I know that because there are 2 elements in the periodic or in the first period of the periodic table. So if I'm writing the orbital diagram for scandium, or the electron configuration for scandium, I know that I have 2 electrons in 1s. Then I look across. How many electrons fit in 2s? Well, this block is what we call my S block of the periodic table. So these 2 electrons are in 2s. Then what's next? Well, this is my P block of the periodic table. There are 1, 2, 3, 4, 5, 6 electrons in 6 elements in the P block, and each orbital can hold 2 electrons. That means there can be 3 orbitals in 2p, and it holds 6 electrons. Then I move down to the next period. Again, in my S block of the periodic table, I've got 2 elements, which means that the S block can hold 2 electrons. And I'm kind of running out of space here, apologies. Then I move over, I follow that period all the way across. Then I've got the 3p block. And remember, there are 6 elements in 3p, so it can hold 6 electrons, which means there are half as many orbitals, 3 orbitals. Then I'm finished the 3rd period, so I move down to the 4th period. There are our 4th period, and I'm at the S block, and I can fit 2 electrons in the S block. There are 2 elements, so 2 electrons fit there. Then, this is when things shift a little bit. This chunk is what we call the D block of the periodic table. If we go back and we look at our diagram here, we remember that 3D is just a little bit higher in energy than 4s. So that is what comes after the 4s orbitals. This row right here, this little chunk, this block, is where our 3D orbitals are, shown in the periodic table. So scandium has 1 electron in 3D. Okay, let's move on to making the orbital diagram for scandium. Again, I'm going to show you how to do this using your periodic table as a reference. Well, let's start at the top of the periodic table. We've got the first period and the S block. So 1s. We know each orbital can hold 2 electrons spinning in opposite directions. So there's the electrons in the 1s orbital. Then I've finished the first period of the periodic table. So I move on to the second period of the periodic table. That chunk is in the second period and the S block. So that's 2s. And 2 electrons spinning in opposite directions can go in 2s. Then I follow my periodic table across, and the next block, it's still in the second period, so 2, and it's P. But you'll notice there are 1, 2, 3, 4, 5, 6 elements, and 2 electrons fit in each block. So I should have 3 little boxes here. Okay. Then I've finished the second row of the periodic table. I move on to 3s. Again, there's 2 elements. So 1 square, 1 orbital with electrons spinning in opposite directions. After 3s, I follow that across. and I've got 3p. And again, there's 6 elements, so I need 3 orbitals to hold 6 electrons. So there's 3p. After 3p, I follow my periodic table across. Then I've got the 4s block. There are 2 elements in 4s, which means I need 1 square, because each orbital holds 2 electrons spinning in opposite directions. Then we're going to move on. Next, though, we've come to the D block. You have to remember, though, because of the allowances for our orbital numbers, this is the 3D block. Think about it for a second. How many squares should I draw? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements, which means I need space for 10 electrons, which means my D block has 5 orbitals. So this is 3D. And scandium only has 1 electron in that 3D. Okay, so you can use the periodic table to help you remember how many orbitals are in each orbital level and what their numbers and names are. Here we've got the S block. Here we've got the P block or D block. Here we've got the P block. And down here, that's the F block. If you think about this, count how many electrons or how many elements are in each period of the F block. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So when I'm drawing the F block, there needs to be 7 orbitals. And this periodic table on the next slide shows things blocked out a little more clearly. You can see that the first 2 groups of the periodic table are your S block. Then, over on the right-hand side, the last 6 elements in each period are in the P block. In the middle, you have the D block and the F block. And this periodic table shows you the same thing, but it's got the numbers included and a little bit of a difference with hydrogen. So remembering these trends will help you complete those orbital diagrams as well as the electron configurations. Okay. A couple things I want to point out. When you go through and draw the electron configurations and the orbital diagrams, you probably went through and did things very methodically, and that's great. But you should know that there are a couple of exceptions. Chromium, for example, element 24, and copper, element 29, don't fit the expected trends. For chromium, if we were drawing our electron configuration for chromium, take a second, check your sheet, your worksheet from Friday, the second one, see what you wrote for chromium. Sorry, having a hard time finding my pen here. Okay, so if you look at your sheet, you probably wrote for chromium that chromium's noble gas before it was argon. And as you look across, you should have wrote for S2 and then 3D4. Turns out, though, that's not actually what the experimental evidence shows. Instead of chromium being 4s2, 3d4, in reality, it's got this electron configuration. Chromium is more stable with only one electron in the 4s orbital and 5 electrons in the 3d orbital. So the orbital diagram for the end of chromium actually looks like this. It is more stable with a half full 3D shell rather than having a full 4s and a partially filled 3D. So that's the electron configuration for chromium. Copper, also interesting. If you look at your sheet for copper, you likely wrote argon, 4s2, 3D, 9. But in reality, copper is more stable again with only one electron in the 4s shell and a completely full 3D shell. So sometimes these electron configurations won't follow the expected trend, especially if there's a way to end up with either a half full inner shell or a completely full inner shell. So those are some of the exceptions. Okay, before we go any further, I would like you to pause here and try and use your periodic table to draw orbital diagrams, the little boxes, for tungsten, as well as electron configurations for tungsten. Element 74. Okay, pause, try it on your own. Okay, so here's tungsten, element 74. I'm going to try and have enough space down here to draw my orbital diagrams. It's going to be tight, but we'll try this. So I know that I should have 1s, then, so this is my S block, remember? 1s fits 2 elements, so 2 electrons, therefore 1 orbital. Then I have 2s, again, 2 elements in the S block, so 1 orbital. Then I'm going to end up with the 2p orbitals. 2p has 6 elements, therefore 6 electrons, therefore 3 orbitals, because each orbital holds 2 electrons. Okay, then we would move on to 3s. Again, 2 electrons can go in the 3s, so 1 box, and then we move on to 3p. And 6 electrons go in 3p, therefore 3 orbitals. After 3p, we have 4s. After 4s, now we're moving into the D block. And remember that it was, we haven't had any D orbitals yet, and it has to be therefore 3D. There should be 5 3D orbitals because there are 10 elements in 3D. After 3D, well, then we move on to 1, 2, 3, 4s. Again, 3 elements, 4s. Okay, after 4s, what do we have? We have 5. Sorry, that was 4p. After 4s, we have 5s, followed by, so here's 5s. this would be 4D. This was my 3D. This is my 4D. Again, 10 elements. So 10 elements means we have 5 orbitals. After 4s, then we have 5p. And after 5p, we finish that period, we move on to 6s. So all of these would be completely filled. And I like this all the way through. Here's where it gets interesting, and I didn't save enough space, so I'm going to start writing up here. So after my 6s, notice that the F block is actually inserted right in there. Like you could literally cut out this chunk of your periodic table, split your periodic table in half, and put the F block in there. So if you think through your orbital, your quantum variables, this is our this is our 4F orbital. And if you're wondering why it's 4F, think through your allowed quantum numbers. When n is equal to 4, well then L can equal either 0, S, 1, P, 2, D, or 3, F. So this is the 4F block. So 4F has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements in it, which means it needs space for 14 electrons, which means there should be 7 orbitals. 1, 2, 3, 4, 5, 6, 7. And after 4F, then we're going to end up with 5D. Again, it's a D block, so there should be 5 orbitals, because the Ds have 10 electrons or 10 elements, which means we need room for 10 electrons, which means there are 5 orbitals. So when I'm filling these last orbitals, 6s, completely full. 4f, also completely full. Then 5d, as I look across, has 1, 2, 3, 4 electrons in it. Note that those electrons are unpaired. We don't pair them right away. We fill empty orbitals first. So there's 5d. Okay, so there's how we would write the orbital diagram, except you'd save yourself way more space. So you could do this, and all of these would be completely full, and so on. There's how we would write the orbital diagram. If I was trying to write the electron configuration, I might ask you for the long form or the short form. If I'm looking for the short form, I find the noble gas before tungsten. That's xenon. And then afterwards, I know I have 2 electrons in 6s. I have 14 electrons in 4f. And I have 1, 2, 3, 4 electrons in 5d. So there's my short form electron configuration. So I will give you some more time to practice these in the homework questions, but I want to spend some time talking about patterns. First off, elements in a group have similar chemical properties because they have the same number of valence electrons. It's those outermost electrons that are the most reactive. Those are the ones most likely to participate in chemical reactions. So ones with the same number of valence electrons tend to have the same patterns in reactivity. For the main group elements, the last numeral of the group number is the same as the number of valence electrons, except for helium. So like phosphorus has 5 valence electrons because it is in group 15, and the second number of 15 is 5. Then the N value of the highest occupied energy level is the same as the period number. For example, tungsten, its highest occupied energy level or number was 6, so it's in period 6. Then the square of the N value equals the total number of orbitals in that energy level. So when n is equal to 1, well, 1 squared is 1, so that's 1 orbital. When n is equal to 2, well, 2 squared is 4, that's 4 orbitals. Those are 2s and the 3 orbitals in 2p, right? Okay. When n is equal to 3, the 3 squared is 9. So that's 9 orbitals. Those 9 orbitals would be 3s, 3p, and then 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 orbitals. Wait, why are there only 8 elements in period 3? Well, think about it. You years ago remembered that rule 288 when you were drawing Bohr-Rutherford diagrams? But the reason you had to remember that rule, even though there should be 18 elements in the third period, is because these 3d orbitals, they're just slightly higher in energy than the 4s. As a result, the periodic table looks the way it does. The 3d orbitals are actually slightly higher in energy than 4s. Okay, so in grade 11 chemistry, you spent a lot of time talking about trends in the periodic table. And we looked at those trends, and then we noticed there were some exceptions, but we just kind of ignored them. The first trend you probably looked at was the size of an atom, or atomic radius. Technically, it's the distance between the nucleus and where the valence electrons are located 90% of the time. So think this through. You likely learned that the size of the electron decreases from left to right as you go across a period, and it increases as you go down a group. And you probably learned that it decreases in size as it goes across because there are more protons added to the nucleus as you go across a period in the periodic table. Those more protons mean more positive attraction for the electrons. The more positive attraction for the electrons pulls the electrons closer to the nucleus. And that trend holds true as we go across the first 3 groups of the periodic table. You start to notice, though, when we see the transition metals in the D block of the periodic table, or the lactamides and anthonides in the F block of the periodic table, that trend is really a lot less obvious. And that's because those extra electrons, they're no longer going to an outside shell of the radius. Instead, they're going to an inside shell because 3D is lower in energy than 4s. You'll also notice that the other trend you learned was that as you go down a group, atomic radius increases. And that's because you're adding a new energy shell each time. And you see that this holds very consistent across the S block elements or the P block elements. but it's less consistent in the D and F block elements because you're adding again to inside shells rather than outside shells. So atomic radius increases as you go down because you're adding to shells, but the trend doesn't hold for the transition metals because you are filling the interior orbitals, not exterior ones. So, the factors that affect the atomic radius, well, changing the value of n. As you increase n, size increases. That's what the n variable means. Second, the effective nuclear charge, the net attraction between the electrons and the nucleus. The more protons you have there, the more positive force you have pulling the negatively charged electrons in closer. And then transition metals aren't going to exhibit the same general trend as the main group elements. And the reason for that is that electrons are added to energy levels, the d orbitals and the f orbitals, rather than the outer energy levels. So the effective nuclear charge doesn't change very much. Okay, then our second trend that you likely learned about in grade 11 chemistry was ionization energy. If you took chemistry with either me or Mr. McInnes, we probably made you do an assignment where you graphed ionization energy and asked you a bunch of questions about the trends you saw. Well, remember that ionization energy is the amount of energy it takes to pull off the outermost electron from an element in its gaseous state. So as you the first ionization energy is how much it takes to remove the first electron. The second ionization energy is how much energy it takes to remove the second and the third electron, and so on. And when you think about these trends, remember that in general, you learned that ionization energy decreases as you go down a group. It takes less energy to remove electrons that are farther away from the positive attraction of the nucleus. As you add shells, the ionization energy decreases. Then you probably learned that as you go across a period, ionization energy increases. The closer those electrons are to the positive charge of the nucleus, the higher the ionization energy. The closer it is to having a full shell, the higher the ionization energy. So let's take a look at this graph. And we see that's what's happening. Hydrogen has a very high ionization energy because it only has one shell, and those electrons are pretty close to the nucleus. As you go down the alkali metals, so hydrogen, lithium, sodium, potassium, etc., we see that in general, ionization energy decreases as they get larger in size. Same thing if you look at these peaks, which are noble gases. Ionization energy decreases as they get larger in size and the electrons are farther from the nucleus, and there's more shells in between the nucleus and the valence electrons. Okay, then let's look across a group. So here would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's across our second period. And we see that in general, ionization energy increases across this period. And this is the trend you saw in grade 11, but we didn't talk about these little blips. Let's see what's going on with those little blips. So I'm going to draw some orbital diagrams. So here's 1s, here's 2s, here's 2p, etc. So for lithium only has one electron, lithium has a full 1s shell and only one electron in 2s. Think about that. If I get rid of that one electron in 2s, then lithium has a full shell. It's very stable. As a result, it's very easy to remove lithium's electron in 2s. That's why the ionization energy, or the first ionization energy of lithium, is so low. Then, if I have beryllium has two electrons in 1s and two electrons in 2s. Now, it's got a full orbital. It takes more energy to remove beryllium's electron than it did for lithium. This is just a little bit more stable. Um, so that's why this has a slightly higher ionization energy. But next we have boron. Boron has a full 1s, a full 2s, and then just one lonely electron in 2p. It doesn't take very much energy to remove that electron in 2p. In fact, boron, its ionization energy is lower than beryllium's, because beryllium had an empty 2p and a full 2s. So it was easier to remove this electron than it was to remove this paired electron in a full orbital. That's why beryllium has a higher ionization energy than boron. The next element I want to look at is what's going on up here. So here was boron, and then we would have carbon. This is going to be nitrogen, and this is oxygen. So if I look at nitrogen, nitrogen has a full 1s, a full 2s, and 3 electrons in 2p. It's got a half full shell. And this is actually a pretty stable configuration. Nitrogen is pretty stable like this. Whereas if we compare with oxygen, oxygen has full 1s, full 2s, and only one electron pair in 2p. This isn't all that happy. It's not all that stable. It takes more energy to remove one electron from nitrogen, which has this half full stable shell, than it does to remove that electron from oxygen and give it the same electron configuration as nitrogen. This is less stable than this. As a result, the ionization energy for nitrogen is just slightly higher than it is for oxygen, because a half full shell is more stable than this weird asymmetrical business going on. And then lastly, let's just jump all the way to neon. If I have neon, well, then neon has a full 1s, a full 2s, and 6 electrons in 2p. It's got a completely full n equals 2 orbitals. So neon is very stable like that. It requires a lot of energy to remove neon's valence electron. Okay, so this really helps to explain these blips in ionization energy as you go through the periodic table. So we won't focus a lot on the trend in electron affinity, but just remember from grade 11, the electron affinity is the change in energy that occurs when an electron is added to a gaseous atom. So now we're adding electrons. And we see that this trend is a lot more variable than the trend in ionization energy, but there's some general things that occur. So trends for electron affinity are more regular than ionization energy. Groups 16 and 17. So 17 is the halogens. Those all have high ionization energies and also high electron affinities. So this group and this group, high ionization energy and also high attraction for electrons. Groups 1 and 2, so that's the alkali metals and the alkali earth metals. They have pretty low ionization energies and low electron affinities as well. And then lastly, group 18, the noble gases, has the highest ionization energy and very low electron affinity. And that makes sense because they have full shells. Okay, your job. There's some extra reading and then some textbook questions to try. Then go through and identify the group number, period number, and orbital block for these elements. And think through these last questions on trends in the periodic table. As always, there are, well, not always, but most of the time, there's an answer key in that blue binder on the side of the classroom. Okay, thanks for listening.